So, hello everyone, good evening, and welcome to Uncovering Azure's Silent Threats, a journey into cloud vulnerabilities. So, before we begin, let's take a look at our guide. So, my name is Nitesh, and I'm from Sikkim, a small state in India, and I'm really honored to be here at Nullcon, as this is my first time as a speaker. I work at Trend Micro with a focus on cloud and container threat research. Sometimes I also delve into vulnerabilities around them and just report it. So at Trend Micro, I have been building honeypots, doing threat hunting, threat modeling, and that's all the jazz that is all about. I've been in the threat research space for around 2.5 years now. Additionally, I have some experience of security operations in the past and threat hunting, playing some CTFs, some bug bounties here and there, and VDPs as well. So I'm a member of Null Bangalore. It's an open security community, and I'm really honored that those are the guys that I started off with back in 2019. So 2 fun facts about me. I wrote my first song in 2018, but my first exploit in 2009. So the exploit was around, basically I could freeze the number of steps using cheat engine in Spider Solitaire just to defeat my dad because he's still very good at it. And sometimes he just figures out how I do it. And the other fun fact is that this is a picture from my last trek that I went on with my friends, where I trekked for 4 kilometers. It's not huge, but I actually have a minor ACL tear, so that was a win for me. Okay, so now that you know a little bit about the guide, so let's talk about the journey. Why are you here? You're here to go on a journey of finding some cloud vulnerabilities in one of the hottest machine learning as a service offerings out there. So I'll be taking you on a journey in the form of a couple of chapters. We'll go through some introduction on what we are going to talk about and the issues we uncovered during our journey in the form of 4 main chapters, dropping to the conclusions and some takeaways. Just a note, this is an expanded version of the session that was presented at Black Hat USA this year. So this is a talk about the security issues in the platform itself. So let's begin the journey. There has been some buzz around cloud service providers fixing vulnerabilities reported in services based on Jupyter Notebook. So is there something off or something fishy with Jupyter Notebooks in general? So I pack my bags and I head to the Azure portal and search for services based on Jupyter. And I'm greeted by this one interesting result about running Jupyter Notebooks in a workspace. And folks, this is where it all started. So in 2019, there was a prediction in a Gartner report which talks about a 5-time increase in the usage of cloud-based AI services by 2023. And in 2023, it kind of makes sense as companies are seeking to use AI in their products, services. They want to create ChatGPT-like chatbots. They want to train LLMs on their own custom data sets. And when ChatGPT was released, I was quite curious to know what does the underlying platform look like. And this video clip from May this year kind of makes sense now. So the AI offering in Azure looks something like this. On the top, we have the applied AI services. So these are the problem-solving services offered by Azure. This is followed by cognitive services, which are basically the machine learning models provided as a service. And everything that you see in the highlighted box in red is actually built on top of Azure Machine Learning Service that we are going to take a look at. So we'll go through some basics first. So AML, Azure Machine Learning, is a mammoth of a service. So we'll go through some simpler terms to understand. So it uses a mix of user-managed and Microsoft-managed services to function. And it's a machine learning as a service offering. Like we have SaaS, it's called machine learning as a service. So in AML, you create a workspace, which is like a centralized place to manage all your ML-related activities and artifacts. You can access a workspace using browser, VS Code, or the Azure CLI, the Azure ML API as well. But what do you do on a workspace? You basically work. You can create Jupyter Notebooks, you can run your experiments, you can create and import datasets, you can create your training and inference environments, you can deploy your machine learning models as an endpoint, and you can do everything just from the browser itself. Like, that's possible. So the workspace is actually dependent on certain other Azure services on the user's end. So when you create a workspace, the resources for these services are created except for the container registry. So it's not mandatory to have an ACR configured to basically work with a workspace. In AML, users or data scientists, they would perform MLOps, and these are the various compute targets that are provided. So on these targets, you will be running your Jupyter notebooks, training scripts, or you can host your models as an endpoint. So for the cluster, so you can have a managed cluster of virtual machines with multi-node scaling as well, and these can be GPU enabled. You can have Kubernetes clusters, so you can attach existing KX clusters based on AKS, or you can have your on-premises onboarded as well. Attached compute, so you can attach virtual machines, Databricks or SD Insight resources to perform your training and inference. And specifically for this talk, we focus on compute instances. So compute instances are basically managed Ubuntu virtual machines that reside in a Microsoft subscription. By managed, we mean that the resources are managed by Microsoft. So like patching of the host OS or fixing any issues if they are found in compute instances, those are taken care of by Microsoft. So it already comes bundled with a lot of tools used by developers such as Jupyter, VS Code, Docker, Python, other deep learning libraries, etc. This is where you can run your code and you can perform your model training. So each workspace uses a storage account which contains your machine learning related entities. To access data in a storage account, you use something that is called a data store, which are basically a reference to a workspace's storage account. They help in storing, they help in avoiding storing access keys or SAS credentials in your scripts. So you can simply refer to the storage account using the data store, and you don't need to like plug in your credentials in your scripts. And so basically you can refer to the file shares or the blob containers, and that is exactly where you store your notebooks, datasets, logs, models, and everything. So these are like the storage side of things for machine learning as a service in Azure Machine Learning. So you can browse the storage account using the Azure Storage Explorer, and you can view the file shares and blob containers that are referenced by the default data stores that are created. So here in the screenshot, you can see the ones in blue, the workspace artifact store. So that's the name of the data store and the type of storage it references. So in this case, it references Azure Blob Storage. And under blob containers, you can just zoom in on the two highlighted items, Azure ML and Azure ML-blob store, which will be relevant later. So here we have the data store name as workspace working directory. The type is file share, and the file share name it references is like code followed by the UUID. So this is just an example. Additionally, data stores in Azure Machine Learning, they support credential-based authentication for file shares. This basically means that if you want to work with file shares using data stores, you will be using a combination of a username and a password, where the username is the storage account's name, and the password is the storage account's primary access key. Additionally, multiple users can create compute instances in a workspace, and by design, there cannot be two owners for a compute instance. Also by design, any user can access other users' file in the same workspace because it's a shared environment. So the file share of the storage account for a machine learning workspace is actually mounted on each compute instance in the workspace. So with this very detailed background and a very simple introduction of AML, we begin with the first episode where a data scientist is actually looking for their keys. Did you see my keys? While examining the different folders and the files created on a compute instance, we come across a specific directory structure which looks like this. Now, this directory structure is of Azure Batch. So we now take a look into what Batch is. So using Batch, you can run large-scale workloads in Azure. So for example, you need to process images at scale by distributing the workload. So you can use you can basically use Azure Batch. And these are some basic terms to understand as we proceed. Because remember, it's a journey and not all processes are beautiful. So compute nodes are basically Linux or Windows-based virtual machines. A group of nodes is called a pool. And the group of nodes are basically where you have a couple of VMs in the same pool. So that's like a logical container. Then you have something that is called a job. A job is like a collection of tasks that are run on a pool, and a task is an individual, like the individual unit of computation for a job. So you can think of tasks as commands executed on nodes that are in a pool. Okay, and for each task, you can actually monitor and download the output logs of the tasks. So in batch, you have a concept of a start task. So basically, the start task runs when a node starts up, and the files, the configurations, the output of the task are stored in the path in blue. The error logs and the output logs that are generated based on the output of the start task are logged as well in standard error and standard out. As we previously saw, the file share is mounted on a compute instance. So we had a question. How is the Azure file share being mounted on the compute instance? Since it uses credential-based access, it would be interesting to examine if there are any credentials being stored or logged somewhere. So what we found was that the output of the start task is logged in the standard error and standard out, where the standard error logs contain the username and the password, that's the storage account name and the storage account's primary access key, in cleartext. And since this command runs as sudo, it also gets logged in the authorization logs. So we reported these two instances to Microsoft because these were credentials being logged in cleartext, and we waited. Few days later, we came across an instance where the password field of the entire command line was masked. So note that the commands executed in the start task are defined by Microsoft. The user does not define it. So this was the fix. So we noticed the fix attempt after our reporting. Then we had a query to ourselves. What if there are more such instances of credentials being logged or stored in cleartext on compute instances? Hence, we started looking for more such occurrences. So AML uses certain agents to manage compute instances. So basically to diagnose, monitor, make sure that the compute instance is healthy. And these agents are installed on all compute instances and they are maintained by Microsoft. So the agents are located in the path in blue. So it's under the working directory and the start task. So these agents need configurations to perform actions. And these agents run as daemon services. And the configurations are provided in the form of environment variables. And the environment variables are stored in a file. And the file is under DSI directory in the working directory. Okay. What we found was that for two such agents named DSI mount agent and DSI idle stop agent, we found the storage account key in cleartext in an environment variable that is supposed to go to the process and all the underlying processes named passwd. But why is the environment variable named like passwd? It could have been storage account key or something else as well. So it turns out that the password argument for that sudo mount command, it can be actually supplied as an environment variable. Nevertheless, all the instances of storage account credentials being logged or stored in cleartext on compute instances were fixed after our reporting. And that brings us to chapter 2. Since credentials being logged or stored in cleartext was acted upon and fixed, we had a thought. Are there credentials coming in on the compute instance? And with that, we begin chapter 2. Wait, is that my token? So a user can access a compute instance right from their browser itself using Jupyter Notebook, Jupyter Lab, a browser embedded terminal. So yeah, and these requests are actually proxied to the compute instance by a load balancer / proxy in between. So let's say if you want to access Jupyter Lab on a compute instance named AML in the East Asia region, this is the URL that you need to go to. And obviously you need to have your role-based access control permissions as well. So this is how Jupyter Lab looks on the browser side of things. And this is how the browser embedded terminal looks in the Azure ML Studio. Oh yes, the default user, Azure user, can assume root privileges without needing a password. And there is no security boundary here when you are root on the compute instance itself. So we'll use this bit later. So these browser-based terminals can be accessed by a user with the proper role-based access control permissions. And the authentication flow for a client accessing AML looks something like this. So the client logs into Azure AD, or is it like too early to say Entra ID? I'm not sure. So they log into Azure AD and they are presented with the ARM token, the Azure Resource Manager token. And using this token, the client can talk to the Azure Machine Learning Service. Now the Azure Machine Learning Service creates another AML token, and this AML token is scoped to the workspace itself. and you can perform your AML actions using this token. So this is how it looks. All incoming requests to the compute instance are received by an Nginx proxy listening on a fixed port, that is 44224. So it has an SSL enabled, and it also verifies the client-side certificates presented at that time. And there are some checks on the subjects and the issuers of the client-side certificate. Followed by, the proxy checks whether a header named XMS target port, separated by hyphens, contains a numeric value. And if not, it returns a 401. And later, based on the URI that we are trying to access, so these URIs that are API LS, API kernels, these are related to Jupyter-related APIs. The request is upgraded to a WebSocket. So this is for the terminals as well. And all the requests are finally passed to the proxy pass directive in the proxy host variable, which is set on the second line with the XMS target port. So basically what this means is, for every request that is incoming on the compute instance, this header will be populated. This request is received by the Nginx proxy listening on this port 44224. And based on the value of this header, the request will be forwarded. So in this case, 8888 is the default port for Jupyter Notebooks. And the interesting bit here is all the access attempts, and if there are any error logs generated, they are saved by default in these files. Okay, so we found this issue using our good old friend called TCP dump, where we wanted to view the network capture, like what happens when you close a terminal, or what happens when you create a terminal. So when a user terminates a Jupyter terminal, a GET request is sent, followed by a delete request. So this is fine, but if you notice, there is a token parameter, like a token URL parameter in the GET request itself, which starts with EYJ, and if your spidey sense is tickling, it's a JWT. And by decoding the JWT, we were able to figure out the claims and the values. Turns out we have the JWT of the compute instance owner. And this was getting logged in the access logs because it was in the URL parameter named token. So but why was the token even there in the first place? So in the documentation of Jupyter Server, we see that an authentication token can be provided in 3 ways. So one of the ways is to do it via an authorization header. The other is to pass it as a URL parameter. And the third is you can just put it in the login form of the password field. So, and since Nginx logs the access attempts, the the JWT of the compute instance owner was also there in the access log. We reported this issue to Microsoft and they promptly fixed it as well. So we reported these 5 instances of credentials being logged in cleartext and they were fixed. But what could go wrong? After all, these are just credentials being logged or stored in files on compute instances. What is so risky about it? So developers have been observed to share error or debug logs from their systems on public platforms like GitHub. If they are not quite aware of the fact that these artifacts may at times contain credentials, that too in clear text, that's a silent risk that they are being exposed to. In this example, we see the request between two developers that are requesting for some batch error logs, and this is the exact file on which we found the storage account credential in clear text. However, this instance is from 2018. So this is a recent one. Does anybody recognize this URL? Okay. So we have a storage account name in this URL. So basically this, when you send a request to this URL, you are able to download this file named FGVC aircraft, the *gz file. But there's a story behind this. So this is the storage account name followed by the accessible services. So using this URL, so basically it has the SAS token appended and you can access the blob, file, queue, table, the types of storages. And the APIs that are accessible are the service container object level APIs, followed by the permissions that you have on the storage account. So these are the read, write, delete, list, and all those. So basically it's the root of the storage account. And the expiry of this token is basically 2051. So researchers from Wiz found this issue in June this year, where an overly permissive SAS token was shared on public GitHub repositories of Microsoft. So this is a very recent finding, allowing them to use this token to access 38 terabytes of information in the storage account, including some confidential information related to Microsoft. And by default, the storage accounts that are created using in Azure Machine Learning Service, they are public by default, publicly accessible by default. And based on the blob container names from their blog, it's highly likely that these blob containers are of a storage account related to an AML workspace. So this, if you notice, the Azure ML-blob store and Azure ML, these are the same names that we saw when we were exploring the storage account using Azure Storage Explorer. Supply chain attacks and dependencies. So dependency confusion attacks are an attacker favorite, and basically the attacker control code executes in the victim's environment. But in this case, the nightly build of a popular library called PyTorch was compromised last year December. And the malicious binary would then exfiltrate the credentials from files and environment variables as well. So if an attacker is able to compromise a file share, then they can actually trivially compromise the entire storage account and the entire workspace too. Let me show you how. Consider a scenario which might be likely to happen. So there is a workspace with 3 data scientists, each having 1 compute instance. By design, we know that each workspace user's files are stored in the same Azure file share that is mounted across all the compute instances. So if an attacker gets hold of a user, which is a very high degree of a compromise, or a compute instance which had these credentials being stored or logged in cleartext, or the file share where you have your Jupyter notebooks, scripts that are run on compute instances and compute clusters as well, the whole workspace should be considered to be compromised. Now picture this with a scenario where the users could view each other's JWT token as well because they were getting logged in the Nginx access logs. Suddenly, because of the risks and the features, the issue becomes massive. Additionally, according to the docs, data stores provide a way to secure your connection information, such as your storage account access keys and SaaS credentials. And using them, you don't need to store credentials in your scripts when you're using them. And that's a very cool of a feature. However, if the storage account key itself is getting logged or stored in cleartext, in auth logs, error logs, environment variable files on a compute instance, that kind of creates a difference. And remember, the default user, Azure user, can easily assume the pseudo permissions, so that's not even a boundary here. Okay, so now the same issue of credential logging may have been lurking in your environment as a silent threat, like a ticking bomb. But on Valentine's Day this year, Microsoft released the CVE for this finding, so kudos to Microsoft for that, for accepting the bug and triaging and fixing it as well. Now, the JWT is not observed to reach the compute instance after our reporting, and the storage account access key is not logged or stored in cleartext in any of the files. Some takeaways from the first episode: be it logging or storage of credentials in cleartext is bad. It's very crucial to close loopholes and lower the risk involved in case of a compromise, especially when we have been observing like cloud-focused threat actors going after or just loving credentials stored in files. From the design of such environments, you need to also be aware of the associated risks. So, and also you need to review the open source configurations like before you are using them. So for example, forwarding the supplied JWT of the user to the compute instance was still okay. But logging the token, definitely not. So URL parameters shouldn't contain sensitive information, as we never know the inline components like proxies that they pass through. Additionally, developers need to be very aware of possible security implications that may emanate while sharing information on public platforms. So the issue of credential leakage can turn out to be critical, especially when users are not even aware of them, like we saw recently in the Microsoft's case of 38 terabytes of an AML storage account, highly likely. With that being said, now we embark on the third and almost final chapter of spying the scientist. So in Azure Machine Learning, you can create compute instances in virtual networks. So you can specify the virtual network and a subnet during the creation of a compute instance. And this can be an observed scenario where the training environment needs access from or to other resources via private networks and not over the internet. And using VNets, this is also a recommendation from the documentation from Microsoft. Okay, so simple environment would look like this. The VM lies in a virtual network, and on the same virtual network, we have a compute instance. Let's say the Azure VM on the user's end gets compromised. What could someone from the Azure VM do on the compute instance? were there any ports open on the compute instance? Let's find out. We fired up our next favorite tool, Nmap, and we checked for open ports, and we come across a port that is 46802. Remember, we had the compute instances access as well. So we figured out the process that is listening on this port and taking in the requests or anything. So the process listening is called DSI mount agent. The process runs as root. You probably know where this is going, but just hang on. And we also look up if the binary is open source or if we have any open source code for it, like we have for WA Linux agent or OMI. But we don't find any references as such. So it is a closed source binary. However, we have some debug information to understand the binary a little better. Now we crack open the binary using IDA to understand what is going on, and we come across this function called DSI start API service, and we find that there are some other HTTP endpoints that can be accessed. Just a reminder, no authentication is required for network adjacent resources to access these endpoints on the compute instance. So we start taking a look into the different URLs and what do they do. So the first one basically executes sync command on a file. The second one runs the mount operation, more on that later. The third one views the compute instance's image version, but the fourth one lists any systemd installed services and the statuses as well from the compute instance. So examining the services endpoint, one could list the status of each service installed on the compute instance. Okay. We also see that one could see the logs of any service that is installed in the compute instance. So a network adjacent attacker could basically list down the services installed, the status of the service, the logs for the service, and this could basically aid them in performing some reconnaissance for proceeding with lateral movement once they are already in the environment, or like some similar scenarios, But how bad could it be? So just for an example of what all could be exposed, here's a short little demo. While exploring the installed services on the compute instance, we see that Jupyter is installed as a service on the compute instance. Now this is across all compute instances for users using Azure Machine Learning Service. And for each service installed, we can view the logs. Since we are network adjacent and there is no authentication required, I'm kind of repeating the same line just to emphasize on the things. Turns out, some commands can be viewed that were executed using the Jupyter terminal. And folks, this is where I went, what did just happen? We saw some commands being logged in the logs of Jupyter service. Instead of Jupyter, there could have been some other installed service as well. Simply put, let's say, if a network adjacent if an attacker is on a virtual machine, which is a part of a virtual network, and on the same virtual network, we have a compute instance. The compute instance has a service that is called DSI mount agent, and this service can fetch systemd logs, and it exposes an API on port 46802, listening on all the interfaces, and the user is using Jupyter Lab, Jupyter Notebook, any form of Jupyter to access the compute instance, and the user runs any command as sudo, let's say sudo cat etc shadow. The attacker from the network adjacent resource, that's the virtual machine, they can fetch the logs for any service, and the logs will contain the sensitive information like the command executed as sudo by the user. Now remember the first command that we saw in the entire deck. So it was the sudo mount, and then you have the mount that we are trying to get on the compute instance, where you have the username and the password. So here's a quick demo about it. So we named this vulnerability MLC. So on the top, we have a compute instance where a data scientist is basically running sudo cat etc shadow. On the bottom, we have a network adjacent VM from which we are fetching the logs. As you can see, we just fetched the command that was executed. And now we are executing a command to basically mount a file share, and the same command will be visible to the network adjacent attacker as well. Hence, the attacker could basically see what the data scientist was doing. We reported this vulnerability to Microsoft, and they fixed it as well. And this was a funny information disclosure bug, like an edge case. Now the service does not expose the port on all interfaces and can only be reached over the Nginx proxy that we saw in the second episode, which listens on port 44224. Some takeaways: secret agents may lead to secret bugs and hence an expanded invisible attack surface and hence a silent threat. So cloud service providers also should also look into the attack surface introduced when you are giving features to these agents being used in such environments, as these features at times can expand the attack surface that is not supposed to be there in the first place. So vulnerabilities still exist in cloud agents, and there is a focused need for threat modeling on the features, like I said. Zero trust. So zero trust is hard and it's very crucial for cloud security. But for this case, so do not assume that just because something is already there in your environment that it should have access to other resources in your environment. And deploying training environments in VNets is a recommendation from Microsoft, and this was the edge case that we found. And if you follow the documentation of securely deploying your training environments, you would be using VNets, and you would have been vulnerable to this kind of scenario. And obviously, simulating attacks in such secure configurations may uncover vulnerabilities in the service itself. Okay, so we are at chapter 4. Can you really see me? And obviously, I could not stop myself from putting this up. It's been a childhood dream, I believe, for a lot, I guess. Okay, so let's say we have a virtual machine and a compute instance, and we want these Azure resources to access certain other services. One of the ways is to hardcode the credentials, but credentials in cleartext are bad, and that's not a recommended way from Microsoft as well, so that's a good thing. Microsoft recommends using something that is called a managed identity. So the logic behind managed identities is that, let's say if you want your application to access a resource, the app will first request for a token to work with the resource from a managed identity service, and the returned token will then be used to interact with the resource that the app wants to work with. And the managed identity service is supposed to be can only be reached from the resource itself, just like the instance metadata. And you as a developer don't need to hardcode credentials in your apps or scripts. This is pretty cool, and it solves a lot of problems as well. So managed identities are of two types: a user-assigned managed identity and a system-assigned managed identity. So user-assigned managed identities can be assigned to multiple resources in Azure. So basically they can span across resources. And system-assigned managed identity are just for the resources that we want them to be assigned to. And only that Azure resource can request for tokens, or it is supposed to request for tokens, as we'll see later. So on a compute instance, one can sign in using managed identity using the Azure CLI. And you can assign certain privileges to the resources for accessing other resources. For example, you should not assign a contributor role to a managed identity across some subscription or some resource unless and until you know what you're doing. But I was curious to know, what is the traffic looking like when you do AZ login -- identity? What is happening in the background? So we are back to our old friend TCP dump, because Nmap did not help a lot. And we checked for any outbound traffic when we run AZ login -- identity. And we get this GET request with some interesting headers. So it has a secret header containing some weird value, but it is being sent to a port that is still on the local interface. But from the port information, we pull out the process listening on this port. The process is named Identity Responder D. The process belongs to a service called Azure Batch AI Identity Responder daemon, and it uses a bunch of files with various environment variables. It logs output and errors generated to syslog, so that's helpful. But are we talking about responding identities? It looks interesting. While understanding the binary, we found that the binary fetches the secret and the endpoint from this particular file at etc environment.sso. But how does the final request look like? Because even now we are talking to a local endpoint. There has to be some public request going out. We come across another file that is from where the identity responder daemon is fetching in and looking into this value called cert URL, which is like the region.cert.api.azureml and then everything else. But how does the final request look like? That is the agenda right now. Just for curiosity, I had a moment of deciding whether to dump the process, check the logs, or reverse the binary. Since this is our game, why not do all of it? So this is what we got from the logs, and we can see like the reference to this environment variable file, and this is the request that is being sent out, and the final request looks something like this. So we have a post request which has this body with the cert thumbprint, instance ID, and the resource for which we are fetching the token for, and the compute instance name is the instance ID. Okay, and it uses certain certificate and a private key from this directory here, like the startup tasks and the PEM and the key file. Okay, so the agent talks to cert URL using a pair of certificate and a private key, and it gets the AML JWT in the response. Let's say the certificate and the private key are stolen. Can an attacker use these certificates to talk to the endpoint from non-Azure environments? No. So this was a 401 unauthorized, and we were like, that makes sense. So the assumption is the certificate and the private keys are tied to the compute instance. Okay. And that's a good thing. So that also defeats why I was not able to get the token from non-Azure environments. But return to Castle DSI mount agent. Now we take a look into our good old friend in some depth. This service fetches its environment variables from a file that is DSI mount agent env. This is the one that we saw in the second episode about the environment variable containing the storage account key as passwd. So the agent runs as a service on every compute instance, and the environment variables look quite interesting. We have something cool going on here. Keys, certificates, XDS endpoint, what is happening here? Checking the systemd logs, we see that the DSI mount agent is actually responsible for making sure that the file share is mounted on the compute instance, and it makes these checks every 120 seconds. Okay. But what does DSI mount, like who does a DSI mount agent query? So it turns out that the agent talks to the value that was in the batch AI XDS endpoint using the certificate and private key. And the certificate and private key are from this path here. So this is how the post request looks like. We won't be focusing on the post request URI and everything. We'll just focus on the body of this post request from now onwards, because that is the same across everything that we see now. Okay. So the response for this contains, So the post request URI and the headers are same, and finding the function in this agent named DSI mount agent, the function was get workspace info, and this is cool. The response contains the metadata about the workspace, so this can be considered like the who am I of the workspace. It has the resource IDs, workspace ID, tenant ID, subscription ID, and etc. So later, when we were inspecting the DSI mount agent again, we noticed that the post body can be get workspace secrets. What secrets are we talking about? So in the response, we get the account name and the account key JWE. So we can basically decrypt this JWE in a very different fashion. So I was trying to understand the decryption routine, but then my friend David helped me. So we have two environment variables. One is an encrypted symmetric key and a private key. So these environment variables are stored in these two environment variable files for the middleware agents to get the decrypted symmetric key, and using this symmetric key we can decrypt the previously encrypted JWE to fetch the storage account access key. In short, using the certificate and the environment variable files, you could fetch the storage account access key. Okay, so let's say the certificate, the private key is stolen, and the environment variable files are also stolen. Can an attacker do the same from non-Azure environments? We found that yes, an attacker could do from non-Azure environments as well. So let's call these as jewels of AML. Okay. So when you have a compromise for the storage account key, the first step that is also highlighted and known across Azure users is to rotate the key. So does rotating the key help invalidate the certificates? So this is a demo where I'm showing, where I'm going to the storage account for this Azure Machine Learning workspace. And in this workspace, we have the access key. And I'm copying the access key from, okay. So I'm copying the access key to my terminal. So on this terminal, I have the certificates and the the environment variables exfiltrated already. So I'm able to fetch the storage account key using the certificate. So this is the POC that I have. Now I will rotate the storage account key from the portal itself. And after regenerating the storage account key, now I will synchronize the workspace to basically use this newly generated storage account key. So we'll see that in a bit. Yeah, so we have already synchronized the newly generated key, and now we rerun the POC, and we are able to fetch the rotated storage account key using the same pair of certificates from non-Azure environments as well. So if your jewels are stolen, even rotating the keys don't help, and this is already very persistent. And so are there any other open sesames, like can you find something else? So the get workspace secrets function calls another function that is called generate XDS API request schema. So the idea was to look that let's find out all the cross references to this function, and maybe we can find some more candidates instead of just get workspace info or get workspace secrets. And that is where we stumbled upon a function called get AAD token. AAD token, that tingles a lot of spidey senses. And to figure out how does the request body look like, we just debugged using GDB. And we found that, okay, we can specify certain parameters in the post request body itself. So this is how it looks. So the daemon in this case is identity responder daemon, and it is talking to the batch XDS endpoint. And this is how the request body looks like. And in the response, you have this system assigned managed identity token. So we are fetching the managed identity tokens from non-Azure environments. More on that later. Okay, I have just 3 minutes. So, okay, this was a little out of scope for the talk, but since James Kettle also had that pumped up version of the Nullcon edition, so I just added this one as well. So you can also fetch the user assigned managed identity token if you have the client ID specified as well. So this is also defined in the environment variable files. All of this is happening from non-Azure environments. And as we saw earlier, the user assigned managed identity can span across different resources, and it may be overprivileged at times. So the compromise of the certificate and the key and the files containing environment variables, we can use it to fetch the Azure AD token of any type of identity that is assigned to the compute instance. And we can use the token based on the privileges to possibly move laterally and do all that fancy stuff. But why all of this matters? While skimming through the documentation, we come across this particular statement. By design, only the Azure resource can use this identity to request tokens from Azure AD. But we are using certain certificates to fetch the token outside the resource using some certificates. Quick recap, because there was a lot. So the DSI mount agent talks to the batch XDS endpoint, and it uses certificate and a private key. And using this, they can run a whoami, that's the get workspace info, the storage account's primary access key, and the Azure AD token of any assigned managed identity, and a lot more actually. And so could an attacker if they had the credentials, the certificate and the private key exfiltrated. Let's fetch some Azure AD tokens. So I have a live demo for, no. Okay, how do I... This is the first time I'm messing up on a live demo, and okay, we'll come to that maybe. I'll show you in person if that's okay. So basically I was able to fetch the Azure AD token using GitHub code spaces when we had the certificates exfiltrated. And how do the logs look? So how do you identify whether your certificates have been already exfiltrated? So here's a legitimate activity where you have the JWT of the managed identity assigned to the compute instance, and we are fetching it using the standard libraries. And here's the malicious activity where the attacker is doing the same from non-Azure environments. We were confused with the logs that were generated, and the diffs were very clear. So we don't have any IP address information in the logs, so you cannot figure out whether the certificate was used from non-Azure environments or not, because that is one of the metrics that people gauge on. And from the difference between the attacker-generated logs and the compute instance, like the legitimate and the malicious activity, we don't have a lot of fields to bank upon. The observation, the logs are almost identical. There was missing location information as well. The certificate is valid for 2 full years. And to invalidate this stolen certificate, you need to delete the compute instance. And if there is some over-permissive identity that is assigned to the compute instance and the compute instance gets compromised, you have your certificates exfiltrated, it can lead to lateral movement, privilege escalation. There is no upper boundary there. Some takeaways: you need to have your cloud service logging enabled and in place. The logging for managed identity could have been done better and will probably be done better. You need to scope the identities following the principles of least privilege. And definitely defense in depth with respect to cloud environments is a very good win, as we'll see later. And threat modeling environments for the possible scenarios of compromise can shower some light on the weaknesses that are not talked about. Although it has been over 160 days since we reported our findings to Microsoft, but they are still working on the fix for this. We found some bugs that really make the news and get fixed as well, a bit silently. We tried a few angles and we learned along the way as well. But where do we go now from here? So you need to set up your environment using virtual networks, private links, and private endpoints. Now let's take a look in the episodes. The storage account access key getting logged, the JWT getting logged, the agent exposing sensitive information. All of these could have been combated if you had your defenses in place. And you could also easily eliminate these vulnerabilities or these issues at times. And secure deployment strategies never fail and never disappoint you. In fact, Microsoft made it very easy to go secure by default by offering these network isolation options right from the Azure portal itself. So you can choose the type of network configuration you want. Additionally, you need to monitor your cloud environments for changes, storage account keys getting rotated, public or anonymous access enabled, all of that stuff. You need to set up your logging using cloud native solutions. You can also leverage frameworks like the Azure Threat Research Matrix or the Cloud Storage Security Matrix that is recently out there. Trust but verify. So there's a very different angle of security when it comes to machine learning right now, as companies are targeting to move to cloud. So there's a very different angle to it. You need to verify the integrity of Jupyter notebooks, scripts, your storages, keep your storage safe, and all that stuff. Examine, so this is for the hackers and the breakers here. Examine managed services to find and uncover silent threats in these services. These issues are not talked about much in the news, and there's a lot more to find. And there are a lot of issues that are still there in the pipeline to be fixed as of now. And definitely, you need to implement the principle of least privilege, so you can review the permissions for the users that are allowed to access resources in environments. The SaaS credentials should not be overprivileged and all that basic stuff. Specifically for machine learning environments, one can use the Atlas framework. So this is like the MITRE attack for machine learning as a service environments and systems. So as companies will tend to move towards leveraging AML service, it's important that we don't mess this up. So there is this threat matrix for storage services. I recently saw it, so I included in the slide. So it contains tactics and techniques and basically TTPs that adversaries may use against storage services. So if you're aware of what to protect against, you can build your defenses accordingly. In fact, Atlas also enlists various case studies around simulation and incidents that are specifically focused on machine learning only. And these are two of my favorite case studies. So first one is related to the PyTorch dependency confusion. And the second one is the red team assessment of one of Azure services. So we are now at the acknowledgement. So thank you to my teammates, David and Magno, for helping me out in times of doubt. And ZDI for triaging and the smooth communication of the bugs with Microsoft. And Microsoft as well for taking care of these issues and fixing them and on the way to fix as well. And there are a few more bugs in the disclosure pipeline that we are quite excited about, so stay tuned. It's not a question of if a vulnerability like this gets exploited, but a question of when, and we need to secure our present first. With that, thank you for attending Uncovering Azure's Silent Threats, a journey into cloud vulnerabilities. And let me just see.
Thank you, Nitesh, for an amazing talk. There are a few announcements to make. Again, a reminder, networking party venue is Blueberry Hills at 7 p.m. Shuttle service will be provided from BITS to Blueberry Hills at 6:30 p.m. And the distribution of goodies is happening at registration desk. So make sure to grab your goodies before leaving. We are all set for our next talk.
I'll just take 1 minute.
Oh, so sorry.
60
Yeah, please take your time.
Yeah, so I am on my code space where I have the certificate and the environment variable file exfiltrated. I have a POC that I'm not sharing as of now, but using the let me show you how it looks. Oh, no. Yes. So I have two compute instances for which I have exfiltrated the certificate and the environment variable file as well. So I am on the system assigned manage identity compute instance, and now I'll be fetching the identity token from code space, which is outside the compute instance boundary. So I will use AML dumper, so I can dump these information, and I will fetch the system assigned identity here. So this is how it looks, and you can do a lot of stuff there. You can also fetch the storage account credential. You could also fetch the information about the workspace. So this was the demo that I was trying to show, but something happened, I guess, but yeah, I think that's okay. So thank you for your time. If you have any questions, just let me know.